Well, hello there. Mr. Sutton here, bringing you the Pre-Cal Honors 9-4 Part 1 Homework Solutions on algebraic limits of piecewise functions. For this problem, we're using this piecewise function to find the following limits. For Part A, we're looking at the limit as x approaches 2. Since 2 is not a border value, that means we just have to plug it into the appropriate rule. 2 is less than 3, so we're using this first rule here. So that's going to be 2 times 2 plus 3, or 4 plus 3, or 7. Next, as x approaches 3 from the left. Now 3 is a border value, so that means we have to take a look at the before versus the after rule at 3. If we're approaching 3 from the left side, that means we're using this before rule here, the rule that applies to values of x that are less than 3. So for this one, we have to plug 3 into this 2x plus 3 rule, 2 times 3 plus 3, or 6 plus 3, or 9. And now for the right side limit at 3, we have to use the after rule here, the x squared. So that's going to be 3 squared, which is also 9. And now for the two-sided limit at 3, the way this works, if the left and the right side limits are the same, then the two-sided limit is whatever those limits agree on. Since these are both 9, that means that our two-sided limit is also going to be 9. On this problem, we're trying to find the limit as x approaches -1 for this piecewise function. Since -1 is a border value, we have to plug -1 into both rules for the left and the right side limits. So for the left side limit, we plug -1 into the before rule. So that gives us -1 over 2 plus 3 over 2, which we could simplify to, let's see, that'll be 2 over 2, so 1. Next, we have to plug -1 into the second rule to get the right side limit. So that's -2 times -1 minus 6. That's 2 minus 6, which is -4. 1 and -4 do not match. Since the left and the right side limits do not match up, the two-sided limit does not exist. On this problem, we're using this three-rule piecewise function to find the following two limits here. Now, if you look at both of these limits, limit as x approaches 1, limit as x approaches 2, these are both border values here. 1 is the border between the first and the second rule. 2 is the border value between the second and the third rule. So for both of these, since we're dealing with border values, we have to look at the left and right side limits before deciding on the two-sided limit. Let's start with x approaching 1. So as we approach 1 from the left, we're using this before rule for 1. So we're just plugging 1 into the radical 1 minus x squared. So that's radical 1 minus 1 squared. That's just the square root of 0, which is 0. Now taking a look at the right side limit at 1, that's using this second rule here, the after rule for 1, which always returns a constant value of 1. Since 0 and 1 do not match up, that means our two-sided limit at 1 does not exist. Now moving on to x approaching 2, our left side limit is going to be this before rule for 2, this function, which happens to be the after rule for 1, so it kind of is doing double duty for us here. But the left side limit at 2 is just going to be this constant value 1. And now for the right-sided limit of 2, now we're using the after rule here, this third rule for 2, and that just returns a constant value of 2. Since 1 and 2 do not match up, our left and right limits don't agree, so the two-sided limit does not exist. For this problem, we're trying to find the limit as x approaches 1 for this piecewise function. Since 1 is a border value, we have to find the left and the right side limits separately. For the left side limit, you're using the before rule, this -2x plus 5. So that's going to be -2 times 1 plus 5, which is 3. For the right side limit, we're using the after rule here. So this will be -1 squared plus 4 times 1 minus 4. Let's see here. This is 4 minus 4, so that's 0. So really, it's just this -1 that all of this comes out to. Since 3 and -1, the left and the right limits do not match, that means the limit as x approaches 1 does not exist. On this problem, we're trying to find the limit as x approaches -1 for this piecewise function. Since -1 is a border value, that means we have to look at the left and the right side limit at x equals 1. For the left-sided limit at x equals -1, we're using this before rule here for the values of x that are less than -1. So I'm just plugging -1 into x, which just gives me -1. Now for the right-sided limit, we have to use the after rule So I'm plugging negative 1 into the x here, so that's negative 1 squared plus 2 times negative 1. Well, this is positive 1 when you square it, but then this negative out here makes it negative. So we have negative 1 minus 2, which comes out to negative 3. Since negative 1 up here and negative 3 down here, the left and the right-sided limits do not match. That means our two-sided limit at x equals negative 1 is going to not exist. On this problem, we're trying to find the limit as x approaches negative 1 for this piecewise function. Since negative 1 is a border value, we're going to have to find the left and the right limits by plugging negative 1 into the before and after rules for negative 1. So for the left side limit, we've got negative 1 squared minus 2 times negative 1 minus 1. So this is going to be negative 1 out in front plus 2 minus 1. That all comes out to 0. And now for the after rule, we've got 2 times negative 1 plus 2. That's negative 2 plus 2, which is also 0. Since these match up, since 0 equals 0, since the left and the right match, that means the two-sided limit exists, and it's going to be whatever they agree on, which in this case is 0. For this problem, we're using this big piecewise function to find the three limits here. So let's start with a as x approaches 3. Well, 3 is not a border value, so that means we just have to figure out which interval 3 falls in and use the appropriate rule. 3 is bigger than 2, so we're using this last rule here. We're just directly plugging it in here, 5 times 3, which is going to come out to 15. Next, for part B over here, as x approaches 2, 2 is a border value, so that means we have to find the left and the right-sided limits as x approaches 2. As x approaches 2 from the left, we're using this before rule of x cubed plus 2. This is in charge of the x values before we get to 2. So that's going to be 2 cubed plus 2, which is 8 plus 2, or 10. Now for the right-sided limit, we're using the after rule here, so 5 times 2 also gives us 10. Well, 10 equals 10. The left and the right-sided limits match. That means the two-sided limit as x approaches 2 is 10. And now finally for this last one, as x approaches 4, 4 is not a border value. It just falls in this last rule here. So that means we're just doing 5 times 4, which comes up to 20.
For this problem, we have a function f defined by a piecewise function. We have both the algebraic version of this right here and also a graph of f. So we want to know what the value is as of the limit of x approaches 2 of f of x. A lot of ofs in there. This is the limit of a composition of functions. So just like evaluating a normal composition of functions, we have to start with the inside and work our way out. So we're going to start by considering the limit as x approaches 2 of this inner f of x function. So we do have the algebraic version of that, and we notice that 2 is a border value, which is going to be kind of annoying because we're going to have to consider both the left and the right-sided limits to see if they're the same thing. But we also have a graph of f. So we could actually just do this graphically. So as we consider x approaching 2 graphically, from the left side, we're going to the y value 5. From the right side, we're heading towards 5. So the limit as x approaches 2 of f of x is clearly 5, looking at the graph. And if you're not so sure about that, you could actually plug 2 in for x here. 6 minus 1/2 times 2 is going to be 5. And same thing here, if you have negative 4 plus 6 plus 3, that comes out to exactly 5. Anywho, let's do the next thing. We've got 5 as this inner value here, which basically means we're asking now about the limit as x approaches 5 of this outer f of x function. Okay, well, how can we figure that out? Because on the graph, you'll notice we don't have the x value 5. We might be able to kind of anticipate where this is going, but to be sure, we want to use the function over here that they've defined algebraically. So as x approaches 5, we're using a number that's completely within this last rule here, this x greater than 2 rule. So we're just going to do 6 minus 1/2 of 5. This is really 12 halves minus 5 halves, which is 7 halves, giving us answer choice D.